This bridge shouldn't exist. It hangs 625 meters above a canyon, in a place where building anything was nearly impossible. But the way this became possible is not what you'd expect. In this video, you'll see what it takes to build in a place where over 90% of the land is mountains, where short distances take hours, not because they're far, but because nothing runs straight through it. And solving that problem required something most projects would never attempt. In Guizhou province, flat ground is extremely rare. More than 90% of the landscape consists of mountains, valleys, and deep gorges. For decades, this made movement slow and inefficient. Not because places were far apart, but because the terrain forced every route to bend around it. Roads had to follow the natural shape of the land, winding through mountains, avoiding steep drops, and navigating unstable surfaces. A trip between nearby towns could take hours, not due to distance, but because there was no direct path. The result was isolation, limited access to markets, education, and infrastructure. Entire communities remained disconnected from development. So instead of working around the terrain, engineers started removing it as a limitation. Now here's where things get extreme. This is the Huajiang Bridge, the highest bridge in the world, standing 625 meters above a canyon. That's not just height. It's the kind of elevation where building something like this shouldn't work. The bridge stretches nearly 3 kilometers across a gap that was never meant to be crossed directly. Below it, there's no stable ground, only steep cliffs and a deep canyon that made direct movement impossible. At this location, traveling between these 2 points meant navigating narrow mountain roads, sharp turns, and long detours through difficult terrain, a journey that could take up to 2 hours. Now, there's a way across, right across a landscape that was never meant to be crossed at all. This means the bridge doesn't just connect 2 points, it removes the terrain between them. But if nothing here was buildable before, what did it take to make this possible? Because the bridge is only one part of the system. It connects to the S57 expressway, a 150-kilometer route built through extreme terrain. And in one critical section, engineers didn't go around a mountain blocking the route. They cut through it. Controlled explosions were used to break down large sections of rock, executed in sequences to maintain stability while reshaping the terrain. Heavy machinery then removed and restructured the remaining material, aligning it precisely with the planned road path. This required strict control over elevation, gradient, and structural continuity, ensuring that every segment of the road connected seamlessly. This wasn't traditional construction. It was terrain engineering, modifying the physical landscape to create a path where none existed. This means the route wasn't adapted to the terrain. The terrain itself became part of the construction. But even after creating the path, how do you build something across a gap like that? Because building across a canyon like this isn't just about scale, it's about precision. The bridge consists of 93 steel truss sections with a total weight of around 22,000 tons, but traditional cranes couldn't operate at this height or distance, so engineers used a cable crane system stretching across the canyon itself. Each segment was transported through the air, positioned under tension, and fixed into place. Construction began from both sides and progressed toward the center. Satellite positioning systems ensured precise alignment, tracking every section in real time. Temporary stabilization systems supported each segment until the structure could carry its own load. At this scale, even minimal deviations would have affected the entire bridge. This means the structure wasn't just assembled, it had to meet perfectly in mid-air. And when everything depends on that level of precision, what happens when the environment becomes unpredictable? At this height, conditions don't remain stable. Wind accelerates through the canyon, creating uneven pressure across the structure. Even small changes in airflow can generate significant forces over long spans. To understand this, engineers used wind tunnel testing combined with Doppler LiDAR systems to measure real wind patterns inside the canyon. The bridge also had to withstand seismic activity. Shock-absorbing systems were integrated into the structure, allowing controlled movement during earthquakes. Instead of resisting these forces completely, the design allows the bridge to adapt to them, distributing stress rather than concentrating it. This means the bridge isn't built to resist the environment, it's built to respond to it. But if the structure is constantly adjusting, how do you keep it stable over time? Because once construction is complete, the stress doesn't stop. Wind loads shift continuously. Temperature changes cause expansion and contraction. Traffic adds dynamic pressure across the structure. To monitor this, fiber optic sensors are embedded inside the cables and key structural elements. These sensors measure strain and deformation in real time, tracking how the bridge responds to changing conditions. The data is transmitted continuously, creating a live model of the structure's behavior. Engineers can detect even the smallest deviations before they develop into larger issues. This system operates constantly, not during inspections, but every second. This means problems aren't discovered after they happen. They're identified before they can develop. But once movement across terrain becomes this controlled, what does it actually change? Because what this changes is how distance works. Before, distance was defined by the route. Curved roads, steep climbs, and indirect paths stretched short distances into long travel times. Movement was shaped by terrain. Now, movement becomes direct. There are no detours, no forced slowdowns, no routes dictated by the landscape. The path between 2 points becomes as direct as the distance itself. Travel becomes continuous, without interruption. This means distance is no longer stretched by the route. It starts to collapse. And once time changes like that, what else starts to change? Because this bridge is part of something much larger. Guizhou alone has seen the construction of around 32,000 bridges. Not isolated structures, but an integrated infrastructure system. Highways, tunnels, and bridges working together to overcome terrain. As travel time decreases, access increases to cities, to markets, to opportunities. Entire regions that were once isolated become connected to larger economic systems. Movement becomes predictable. Logistics become efficient. Development accelerates. This means isolation is no longer defined by geography, but by whether connection exists. And once connection reaches everywhere, what do these places become? Because this isn't just transportation, it's transformation. Reduced travel time makes regions economically viable. Investment increases. Tourism expands. Local industries grow beyond regional limits. The bridge itself is also designed as a destination, with viewing platforms, glass elevators, and extreme attractions. It doesn't just move people through the region, it brings people into it. Resources move more efficiently. People move more freely. Regions integrate into larger systems. This means infrastructure doesn't just connect places, it can redefine what those places become. And when geography is no longer the limit, what exactly is?